Nothing travels faster than light. You've heard this your entire life. Einstein's speed limit. Absolute. Inviolable. The cosmic law that everything else in physics has to respect. The universe is breaking it right now. Galaxies at the edge of what we can observe are receding from us at several times the speed of light. Not close to c, not approaching c asymptotically, faster. Comfortably, measurably faster. And Einstein's relativity is not violated, not approximately, not technically, not in any sense at all. How? Because the speed limit applies to things moving through space. It says nothing about what space itself can do. And space is doing something that changes everything about what the universe is, how large it actually is, and what we can ever hope to see. Edwin Hubble is at the Mount Wilson Observatory measuring the spectra of distant galaxies, analyzing the light to determine their composition and motion. Light from a moving source is shifted. A source moving toward you compresses the light waves, blue shift. A source moving away stretches them, red shift, toward longer, redder wavelengths. The Doppler effect. Same principle as a passing ambulance changing pitch. Hubble finds almost every galaxy is redshifted. Almost every galaxy is moving away from us. And, here's the key, the farther the galaxy, the faster it's receding. Not randomly faster, proportionally faster. Twice as far, twice the recession speed. 10 times as far, 10 times the speed. This is Hubble's law. Recession velocity equals h0 times distance. h0 is the Hubble constant, the proportionality factor, the expansion rate of the universe. The obvious wrong interpretation, we're at the center. Everything is fleeing us. We're cosmically unpopular. That's not it. Run the same measurement from any galaxy, from a galaxy a billion light years away, from one 10 billion light years away. Every observer sees every other galaxy receding, with recession velocity proportional to distance. There's no center. The expansion is everywhere, simultaneously. Space itself is growing. The standard analogy, raisin bread baking in an oven. The dough expands. Every raisin moves away from every other raisin, not because the raisins are moving through the dough, but because the dough between them is growing. No raisin is at the center, no raisin is special. The dough is expanding, and the raisins are carried with it. Galaxies are the raisins, space is the dough, and space has been rising for 13.8 billion years. The Newtonian picture of space is a container, absolute, passive, the stage on which physics performs. Newton's space doesn't care what's in it. It doesn't respond. It doesn't participate. General relativity killed that picture. Space-time is physical. It curves in response to mass and energy. It ripples. Gravitational waves detected by LIGO in 2015 are literal oscillations in the fabric of spacetime propagating outward from colliding black holes. The stage has become an actor. If spacetime is a physical thing, and it is, we've measured its ripples, then spacetime can also stretch. The expansion of the universe is the stretching of spacetime. And stretching spacetime is categorically different from moving through spacetime. Here's the distinction everything else depends on. Einstein's speed limit, the invariance of c, the prohibition on superluminal travel, applies to objects moving through space. An electron, a photon, a spaceship, a signal, a causal influence. Anything carrying information from one place to another through space. Capped at c. The expansion of space is not motion through space. When the space between two galaxies grows, neither galaxy moves relative to its local space. They're sitting still. The distance between them increases because the space connecting them is stretching. No information is transmitted. No causal influence is carried. Nothing passes between them at all. The space between them simply gets larger. This is not a technicality. It's not a loophole in the wording. It's a genuine, deep physical distinction between two entirely different things that happen to both produce increasing separation. A galaxy receding from us at twice the speed of light is not violating relativity. It's sitting perfectly still in its local environment. We're sitting perfectly still in ours. The space between us is growing at twice c. If we tried to shine a light beam toward that galaxy, the beam would travel at c through its local space. But the space it's crossing is expanding, and from some distances the beam would never arrive. Not because it isn't fast enough, because the road is growing faster than it can be traversed. Which brings us to the edge. If space expands, and the expansion is fast enough, light from sufficiently distant regions can never reach us, not because it isn't trying, but because the space it has to cross keeps growing. There's a boundary, the Hubble sphere, sitting at roughly 14.5 billion light-years from us, beyond which recession velocities exceed c. Inside that boundary, light emitted toward us is making net progress, slowly in some cases, but it's gaining ground. Outside it, light emitted directly toward us is being carried backward faster than it moves forward, like running up a down escalator moving faster than you can run. You lose ground no matter how hard you go. This defines the observable universe, not the universe, the observable universe, the sphere of space from which light has had time to reach us. Its radius is roughly 46 billion light-years. Wait, 46 billion? The universe is 13.8 billion years old. Shouldn't the observable universe be 13.8 billion light-years in radius? Shouldn't the most distant light we can see have traveled at most 13.8 billion light-years? Here's where it bends your intuition. The photons just arriving now were not 46 billion light-years away when they were emitted. They were much closer, a few tens of millions of light-years early in the universe. But space has been expanding continuously while they were in transit. The source has been carried by that expansion to a current distance of 46 billion light-years. The photons traveled through expanding space, and the total distance their source has moved since emission adds up to 46 billion light-years. The observable universe is larger than the age of the universe in light-years because space was expanding the entire time light was crossing it. Beyond 46 billion light-years, more universe, we don't know how much, possibly infinite. Photons from those regions are either still in transit, haven't had time to reach us, or were emitted from regions so distant that their light can never catch up with the expanding space between us. We will never see them. Not with better telescopes, not with more time. Never. For most of the 20th century, the assumption was clean. The universe is expanding. Hubble confirmed that. But gravity should be slowing it down. The mutual gravitational attraction of all matter in the universe should apply the brakes. The expansion rate should decrease over time. The question was just how much. Would it slow enough to stop and reverse, the big crunch? Or slow but never stop, expansion forever but decelerating? 1998 changes everything. Two independent teams are using Type 1a supernovae as standard candles. Type 1a supernovae, a particular kind of stellar explosion, have a known intrinsic brightness. Measure how bright one appears in the sky, and you know how far away it is. Compare its apparent brightness to its redshift, and you get the expansion rate at the time the light was emitted. Do this for supernovae at different distances, different epochs of cosmic history, and you get the history of the expansion rate. The expectation? Distant supernovae should be slightly brighter than a naive extrapolation would suggest, because the expansion was faster in the past and gravity has been slowing it down. The result? Distant supernovae are dimmer than expected, not brighter, dimmer, farther away than they should be if gravity were decelerating the expansion. The expansion isn't slowing down, it's speeding up, has been for the past several billion years. Something is pushing space apart faster and faster, overcoming gravity, accelerating the very structure of the universe. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for this. The discovery that the universe's expansion is accelerating is one of the most unexpected results in the history of cosmology. What's driving it gets a name: dark energy. The name tells you nothing. It's a label for something that makes up about 68% of the total energy content of the universe, that we cannot see, cannot sample, cannot interact with in any known way, and cannot explain from first principles. The simplest mathematical description of dark energy is Einstein's cosmological constant, a term he added to his field equations in 1917, denoted by the Greek letter lambda. He added it to balance the equations and get a static universe. When Hubble showed the universe was expanding, Einstein dropped it, reportedly calling it his greatest blunder. It wasn't a blunder, it was premature removal. The cosmological constant represents a constant energy density of empty space, a property of the vacuum itself. As the universe expands and matter thins out, this vacuum energy stays constant per unit volume. Its relative influence grows. At some point, it overtakes gravity. The expansion accelerates. Exactly what we observe. The fit to the data is good, suspiciously good. The problem? Quantum field theory also predicts a vacuum energy. Every quantum field has zero-point fluctuations, irreducible ground state energy, even when no particles are present. Add up the contributions from all known quantum fields, and you get a vacuum energy density. That number is approximately 10 to the 12 times larger than the observed value of dark energy. Not off by a factor of 2, not off by 1,000, off by 10 followed by 120 zeros. This is the cosmological constant problem, the largest discrepancy between theoretical prediction and experimental observation in the history of physics, by a margin so enormous it's almost incomprehensible. Something is cancelling those contributions down to almost nothing. We don't know what. Is dark energy a cosmological constant, truly the energy of the vacuum? Or is it quintessence, a dynamic field that evolves slowly over time, with a value that changes as the universe ages? Or is gravity behaving differently on cosmological scales than general relativity predicts? We don't know. What we know, it's real, it's dominant, and it's winning. There's a second problem, and this one might be pointing at genuinely new physics. H0, the Hubble constant, should be a single number, the expansion rate of the universe. Measure it any way you like, you should get the same answer. You don't. Measure it using the cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe, imprinted 380,000 years after t=0. The Planck satellite gives H0 approximately 67.4 kilometers per second per megaparsec. Measure it using the cosmic distance ladder, Cepheid variable stars to calibrate distances, Type 1a supernovae to extend the ladder into the distant universe. The result? H0 is approximately 73 kilometers per second per megaparsec. These two numbers disagree by about 9%, at a statistical significance of roughly 5 sigma. At 5 sigma, The probability of a random fluctuation producing the discrepancy is about 1 in 3.5 million. This is not a measurement uncertainty everyone expects to wash out with more data. It's persistent. It's confirmed by multiple independent teams using different methods. It's called the Hubble tension. Two possibilities. One, systematic error in one or both measurement chains, some calibration mistake that nobody has identified despite years of searching. Two, new physics, something that altered the expansion history of the universe between the epoch of the CMB and today in a way the standard cosmological model doesn't capture. An early dark energy component, a brief burst of additional repulsive energy in the early universe, is one proposal. Modified gravity theories are another. The 2024 data release from DESI, the Dark Energy Spectroscopic Instrument, which has mapped tens of millions of galaxy positions to trace the expansion history, hints that dark energy may not be constant. The data suggests possible evolution in the dark energy equation of state. It's not statistically definitive yet. The cosmology community is watching. If dark energy is evolving, the cosmological constant is wrong, and we need something new. The current expansion, accelerating, fast, but modest compared to what happened before, is not the first time the universe expanded superluminally. And the earlier episode makes the current one look sedate. Cosmic inflation. Between roughly 10^-3 seconds and 10^3 squared seconds after the Big Bang, fractions of a second so small they have no everyday analogy, the universe expanded by a factor of at least 10^². In the time it takes light to cross a proton, the universe grew from subatomic scales to roughly the size of a grapefruit. Then inflation ended, and the standard Big Bang expansion continued. Why propose something so extreme? Because it solves three problems simultaneously. The flatness problem. The universe's geometry is extraordinarily close to flat. The total energy density is within a fraction of a percent of the critical density required for flat spacetime. In the standard Big Bang model, any deviation from flatness in the early universe would have grown enormously over 13.8 billion years. The flatness we observe requires fine-tuning to dozens of decimal places at early times. Inflation solves this. Exponential expansion stretches any initial curvature to undetectable flatness, the way inflating a balloon makes its surface look flat locally. The horizon problem. The cosmic microwave background has the same temperature in all directions, to 1 part in 100,000. Regions in opposite directions in the sky are separated by billions of light years. In the standard Big Bang, they've never been in causal contact. They couldn't have exchanged energy and reached thermal equilibrium. So why are they the same temperature? Inflation. Those regions were in contact before inflation blew them apart. They equilibrated, then expansion carried them to opposite sides of the observable sky. The monopole problem. Grand unified theories predict that magnetic monopoles, isolated north or south magnetic poles, should have been produced in the early universe. We've never detected one. Inflation dilutes their density to effectively zero. Inflation fits. It's the leading explanation for the large-scale structure of the universe. Its quantum fluctuations, stretched to cosmic scales by the expansion, seeded the density variations that became galaxies. That prediction matches the observed CMB pattern. What drives inflation, the inflaton field, a hypothetical scalar field with a specific potential energy curve, has not been directly observed. Inflation predicts a particular pattern of gravitational waves in the CMB polarization, the B-mode signal. it hasn't been detected. The searches are ongoing and increasingly sensitive. If the expansion continues accelerating, here's where it ends. The galaxies of the local group, the Milky Way, Andromeda, the Magellanic Clouds, a few dozen smaller galaxies, are gravitationally bound. They'll stay together. Everything beyond the local group is receding, and as the expansion accelerates, the recession speeds increase. Over the next few 100 billion years, all other galaxies cross our Hubble horizon and disappear. Their light, redshifted to infinite wavelength, fades to nothing. The night sky empties. Stars exhaust their fuel. The last red dwarfs, the most miserly stellar furnaces, burn out around 10 more in 45 years from now. No new stars form. The universe enters a long darkness, broken only by the dim glow of cooling white dwarfs. Black holes dominate. Then, on timescales of 10,060,000 to 10,000,000 years, even black holes evaporate via Hawking radiation, slowly converting their mass to thermal radiation. The universe approaches maximum entropy, a cold, dark, diffuse gas of photons and leptons at near absolute zero temperature. Nothing happens. There's nothing left to happen. Heat death. This is the scenario if dark energy is a constant. If dark energy grows stronger over time, phantom energy, the fate is more dramatic. The Big Rip. Expansion accelerates without bound until the force tearing space apart overwhelms gravity on all scales. Galaxy clusters, then galaxies, then solar systems, then planets, then molecules, then atoms are ripped apart by expanding space. Everything, everywhere, simultaneously shredded. Models suggest this could happen as few as 20 billion years from now. The fate of the universe depends on what dark energy is. We don't know what dark energy is. The DESI data hints it may be changing. The answer is coming, slowly, in the form of galaxy surveys and CMB measurements, and gravitational wave detections, and things we haven't thought of yet. Here's what I find worth sitting with at the end of this. Right now, in this moment, there are photons hitting your retina that have been traveling for over 13 billion years. They left their source before the Earth existed. They crossed billions of light years of expanding space, threading through a universe that was growing the entire time. And they arrived here, now, carrying ancient light from a galaxy that is now so far away we could never reach it, could never signal it, could never know anything about what it's become. The observable universe, the bubble we can see, the sphere defined by the finite speed of light and the finite age of the universe, is not the universe. It's our bubble. Beyond it, more universe. How much more, we don't know. Possibly infinite, regions of space that will never be causally connected to us, where stars are born and die, where, for all we know, physics operates in ways we'd recognize, around which our equations would work, but which are permanently, irrevocably beyond our horizon. The expansion doesn't isolate us from those regions by force, it isolates us by geometry. Space between us grows faster than any message can cross it. Not forbidden, just physically impossible, the way it's physically impossible to travel faster than light through space. The universe is expanding faster than light. That's not alarming, that's not broken, that's space-time being what it is, dynamic, physical, capable of growth that violates no law, because it isn't motion through space, it is the growth of space itself. What's alarming, or rather what's beautiful, in the way that genuinely hard problems are beautiful, is that we can see all of this. We can measure the expansion rate. We can detect its acceleration. We can calculate the size of the observable universe, map the ancient CMB, trace the history of cosmic structure from the first quantum fluctuations to the galaxy clusters we see today. And at the center of all of it sits a number we can't explain. 1000 squared the zero. The ratio between what quantum field theory predicts for the vacuum energy and what we actually observe. That's not a small gap, that's a chasm. And bridging it, understanding what dark energy is, why it has the value it does, why the cosmological constant isn't the catastrophic number our best theory predicts, that's where the next era of physics lives. The universe is bigger than any boundary we've drawn around it. It's growing, faster every day, and most of what exists, we will never see. We're swimming in an ocean that's expanding in every direction, carrying everything we know of farther from everything we don't. And we've only just started to understand the water.